and welcome to 16.4 Calculations Involving Colligative Properties. In this section, we're going to take a look at those colligative properties that we explored in 16.3, particularly freezing point depression and boiling point elevation, and we're going to show you how to do the calculations to figure out how much the temperature is going to change when you add a solute to a particular solvent. Okay. The first thing we have to introduce you to is a new way of expressing concentration. It's called molality. Molality is different from molarity. In this case, let me turn my pen on here. Molality, if you remember, molarity is moles of solute per liter of solution. Molality, which is a lowercase m, is going to be moles of solute per kilogram of solvent. So it's not the total solution, it's the mass of the solvent that you're dissolving the solute in. And one of the reasons why we use this unit is because molality does not change with temperature. It doesn't expand. Well, you can have expansion and contraction, but the mass of the solvent is not changing in any of those cases. So let's go ahead and do some calculations with molality, and you'll see how this works. 16.6 says, how many grams of potassium iodide must be dissolved in 500 grams of water to produce a 0.060 molal solution? Alright, well, so let's go ahead and set up our relationship. Molality, which is lowercase m, equals moles of solute per kilogram of solvent. And so we have 0.060 for the molality. Now, this is in moles per kilogram. And that's going to equal, well, we don't know the number of moles that we have, so we can go ahead and put X in there. And then in terms of the kilograms of solvent, we have 500 grams of water. If you want to change that into kilograms, you're going to move the decimal 1, 2, 3 to the right. So this is actually 0.500 kilograms of water. So we'll go ahead and plug that in. Now we're going to multiply those kilograms over to the other side to isolate our x. So let's multiply. We'll use a dot here. So we're times 0.500 kilograms. We have 0.500 kilograms. Notice that the kilograms are going to divide out top and bottom. We're left with moles, which we're looking for. And x is going to equal 0.5 times 0.060, which will be 0.030 moles of Ki, the potassium iodide. Now the question doesn't ask for moles, it asks for the mass in grams. How many grams? So to go from moles to grams, use the molar mass, something you learned back in chapter 10. The molar mass of potassium iodide is going to be 166 grams per mole. Excuse me. And so when you take 0.030 times 166, you get 4.98 grams. So you take your 4.98 grams of potassium iodide, dissolve it in 500 grams of water, you'll produce a 0.060 molal solution. Okay, let's try the next one. Let's calculate the molality of a solution prepared by dissolving 10 grams of sodium chloride in 600 grams of water. Alright, so again, molality is going to equal moles of solute per kilogram of solvent. Do we know the moles of our solute? No, we know the mass in grams. So if we take our 10 grams of NaCl, to change that into moles, 1 mole has a mass of 58.45 grams. So therefore our molality is going to be 0.17109 moles of sodium chloride. So we'll go ahead and plug that in. 0.17109 moles of NaCl divided by the mass in kilograms of our solvent. Well, we have 600 grams of water. Move the decimal 3 to the right, or to the left, excuse me. So we have 0.600 kilograms of water. for a solvent. And so therefore the 0.17109 divided by 0.6 is 0.285 molal. And that is molal NaCl. Alright, so that's calculating molality. It's just moles of solute per kilogram of solvent. Now there's another way that you can express concentration, and that's by using what's called the mole fraction. Now a fraction, again, is just the part divided by the whole. Well, what part are we talking about? Well, the part we're talking about in this case is the moles of solute in the solution. What is the whole? Well, the whole will be the total moles in the solution, and that's going to include solute and solvent. Alright, so if you have, let's say you mix A and B, so you have B in here, it doesn't matter which way you go, and you're putting A inside of that. If you want to figure out the mole fraction of A, it's going to be the moles of A over the moles of A plus the moles of B. Conversely, if you wanted to know the mole fraction of B, you would take the moles of B, that would be your part, divided by the total, which is still moles of A plus moles of B. That would be the fraction that belongs to B. And of course, those two fractions must add up to 1. So let's go ahead and try a couple out. Ethylene glycol is added to automobile cooling systems to protect against cold weather. What is the mole fraction of each component in a solution containing 1.25 moles of ethylene glycol and 4 moles of water? So the mole fraction, which we use the Greek letter chi, it's actually not an X, it's actually a Greek letter chi, it looks like an X. But the mole fraction of A, then we'll call A ethylene glycol, so let's just say EG for ethylene glycol. That's going to equal the moles of ethylene glycol, which is 1.25 moles, divided by the total number of moles, which would be the 1.25 moles plus the 4 moles of water. So you have 1.25 divided by 5.25, and I'm getting a mole fraction of 0.238. And we'll do the same thing for water. The mole fraction of our water then will be the 4 moles of water over the 4 moles of water plus the ethylene glycol, 1.25. And we get 0.762 as the mole fraction. There's no units on there, by the way. All of the units have divided out. Notice on this side the moles have all divided out. It's a common term. And if you add up, just to double check yourself, if you double check this with this, those do add up to a total of 1, which is what you want in a mole fraction. Alright, let's try one more. What is the mole fraction of each component in a solution made by mixing 300 grams of ethanol in 500 grams of water? Well, again, you still have to do this in terms of moles, so we're going to have to change the grams of ethanol into moles as we will with the water. So let's go ahead and do the ethanol first. We have 300 grams of ethanol. And the molar mass, 1 mole of ethanol, well, you have 2 carbons. So you have 2 times the 12.01, plus you have 6 hydrogens at 1.008, and you have the 1 oxygen. So you have 46.07 grams per mole. So therefore, you have 6.512 moles of ethanol. When you do the same thing with water, you have 500 grams of water, the molar mass is 18.02. And so therefore 500 divided by 18.02 is going to be 27.75 moles of water. So therefore, if you wanted to determine the mole fractions, we'll go ahead and do the ethanol first. The mole fraction of ethanol will be 6.512 divided by the 6.512 plus the 27.75. And if we could do that calculation very quickly here. Plus the 27.75. And it looks like I'm getting for a mole fraction 0.19. And if we do the same calculation over here for the water, you have 27.75 divided by the 27.75 plus the ethanols, which is 6.512. And wrapping up this calculation, we get, as you would expect, 0.81. And just to double check, this plus this does in fact equal 1, so we are correct, or likely to be correct. Alright? In the next podcast, we're going to take a look at doing the calculations for freezing point depression and boiling point elevation. We'll see you next time.